Hi, everyone. In this video, we're going to talk about hydrates and the Hydrate Lab. So a hydrate is a compound that has water contained within its solid structure. So the water molecules are kind of stuck to it. They're stuck either in or around all the ions, and they're not bonded to the structure. The water's not bonded. It's just kind of contained within that. So you can remove it through physical means by just warming it up. Now, the easiest way to warm it up is with the nice hot flame of a Bunsen burner, which is what we're going to do during the lab. So a hydrate consists of water plus some compound, and that compound, when the water is no longer there, it's called an anhydrous salt. You should know that term, anhydrous salt. You can see here, an anhydrous salt is really just any ionic compound that doesn't contain water. And on the right, we see a hydrate. So you can see little water molecules kind of all caught up in between the atoms of the ions there. So really, a hydrate consists of anhydrous salt plus water. Now, not every compound can become a hydrate. Some compounds naturally attract water and some don't. And in fact, you probably know some common hydrates, like those little silica gel packets you see in clothing boxes. That's a hydrate, SiO2. It naturally absorbs water, and that's what kind of keeps water from forming inside those packages while they ship. You sometimes see a color change when you have an anhydrous salt compared to a hydrate. On the left, we see anhydrous COCl2. On the right, we see hydrated COCl2. And the symbol we use to show that it's a hydrate is this symbol. COCl2, and then there's a dot there, and then 6H2O. Now that number can vary, but it's always going to be a nice clean whole number. I guess it could even sometimes be like half, but it's going to be some sort of a number that indicates how many water molecules are surrounding each unit, each formula unit or molecule of the compound. So in this case, there are 6 water molecules for every 1 cobalt-2 chloride formula unit. Showing that a little closer, this is what it looks like for magnesium sulfate. This may be Epsom salt. I think MgSO4 is Epsom salt when it's a hydrate. I can't remember exactly the number. It might be a 4, maybe a 5. So you might even have this in your own house. But what this means is that there are 4 water molecules for every MgSO4 formula unit. And we name this using Greek prefixes, which you see in the table here. So 4 is tetra. You're going to call this magnesium sulfate tetrahydrate. You just stick the tetra prefix in front of the word hydrate. Down here, we see silicon dioxide trihydrate. So 3 is tri. You stick the tri in front of hydrate, just like that. And this dot, it doesn't mean like multiplying or anything. It's just a special symbol we use in chemistry to show that the water is kind of located around it. If you're trying to type this up, the best way to do it would be to go like insert symbol, find the dot, and put it there. Although if you're in a rush, you could just do like an asterisk. It kind of means the same thing. Let's move on to talk about the Hydrate Lab. So in the Hydrate Lab, you're going to be given a hydrate. You're going to be given a sample of a compound that already contains water locked into it. And your goal is to find how much water is surrounding each unit of that compound. In other words, you're finding N. You're going to be given CuSO4 dot something H2O. It might be a 2, it might be a 7, it might be a 1. By the way, if it's a 1, we don't write the 1, you just say dot H2O. But you're solving for N. How many water molecules exist for each formula unit of the copper-2 sulfate? So how are we going to do this? Well, it relies on the idea that because the water is not bonded, all you got to do is heat it and the water is going to disappear. So let's say you're given 7 grams of the hydrate. I'm just making this up. Please don't work out the calculations. It'll probably be nonsense. So you're given 7 grams of the hydrate, which is CuSO4 dot something N H2O. You then heat it up, and we're going to literally use the same crucibles that you're used to from the MGO lab. Now, after you heat it, what's the mass going to do? Well, you may have instinctively said go up, because we've talked about mass going up a lot. Mass went up during the mass and change lab when you heated steel. Mass went up during the MGO lab when you heated magnesium. But in this case, it's going to go down. Why is the mass going to drop? Because the water is going to boil away and leave the crucible. So we're actually going to leave it cracked a little bit. So let's say you heat it and now it drops down to 5 grams. And it's not a hydrate anymore. After the water leaves, what's it called? Anhydrous salt, which is not CuSO4.NH2O. It's simply CuSO4. Well, what's the difference? 2 grams of water. So now you just turn this into moles. You turn this into moles. How do we go grams to moles? Periodic table, just like you're used to. And you're going to now compare those mole numbers, and that should give you a nice clean ratio, which should be N. And again, if you're actually solving this, it's probably going to be some random nonsense answer. We'll go through a sample at the end. Let's talk through the procedure. Here's what you're going to be doing on lab day. This is a very basic overview. Your teacher will probably have more detailed instructions on lab day, but just a gist here. First thing you're going to do is mass an empty crucible plus lid. Then you're going to put your hydrate inside, and you're going to record the mass again. So the difference here will obviously tell you the mass of the hydrate that you're given. Then you're going to burn it. You're going to burn the crucible with the lid slightly ajar for about 4 minutes. This allows the water to escape. You're then going to allow it to cool and record the mass again, including the lid. You always want to make sure the lid's on it anytime it's not actively being burned. Otherwise, water from the air can be pulled back into the hydrate, or into the anhydrous salt, turning it back into a hydrate. Okay. Now, theoretically, that should be all we need to do. You got the starting mass, you burned it, you get the final mass. The problem is we might not know that it's actually done. How are we going to know that it's actually done? Same thing as it was during the MGO lab. Heat to constant mass. So you're going to repeat step 3 until the mass does not change. We're going to heat it to constant mass. Your teacher might have other steps in there too, like you might be physically disturbing it, like you might be poking and prodding and breaking up the big pieces to kind of expose it. But essentially, you're going to heat it until the mass does not change. In terms of calculations, you're simply going to calculate the grams of hydrate you started with through simple subtraction. Calculate the grams of water that boiled away, again, through simple subtraction. Convert this into moles of water. And you're going to calculate the mass of the anhydrous salt that remains through simple subtraction. Convert to moles. So we get moles of number 2, moles of number 3. You look for a nice clean ratio, and you report that as N. So divide the moles of H2O by moles of CuSO4, round to the nearest whole number, which you plug in for N. Let's wrap up the video with a sample calculation. You might want to pause here and try working through it. Let's go through it now. Okay, so the first thing we need to do is find the mass of the hydrate. Well, that should be pretty simple. So we're doing FeCl3.NH2O. The crucible weighs 20. The crucible plus hydrate is 26.57. So the mass of the hydrate is 6.57. It's the difference between the first and second masses. Now we need to figure out how much water left it. Well, let's see what happened. You started with 26.57. You heated it. It went to 25.82. You heated it again. It went to 25.38. Notice the mass is dropping. Now, what does that mean? That means that it was not done the first time. You do burn it again, and it stays at 25.38. So you have successfully heated it to constant mass. This really means that this is a useless number here because it wasn't done. We're not going to use that at all. So it went from 26.57 down to 25.38. That loss of mass was your water. Ooh, look at me, I wrote a unitless number. That was grams of hydrate. So the water is 26.57 minus 25.38. The difference there, 1.19 grams. We're going to turn that into moles. Let's do that after. The last mass we need is the mass of the anhydrous salt, which is just the FeCl3. Now, this should be pretty straightforward. In fact, you just do this minus this. It's the hydrate minus the water. Or you can look at the data, and you could do the hydrate plus crucible minus the hydrate, minus the crucible. Oh, sorry, let me rephrase that again. To find the mass of the anhydrous salt, it would be the crucible plus the hydrate after burning. And the reason I got rubbed up there, this really isn't a hydrate anymore. It's an anhydrous salt. So really it's the crucible plus the anhydrous salt minus the crucible. So 25.38 minus 20 gives you 5.38. Just like 6.57 minus 1.19 gives you 5.38. Yeah. We now have everything we need. We're going to turn the water into moles. We're going to turn the salt into moles. We're going to compare and hope for the best. So to turn water into moles, we divide 1.19 by 18.02. That's the molar mass of water. And I got 0.066 moles of water. For anhydrous salt, that is FeCl3. That's the anhydrous salt. Let's do the molar mass. 55.85. One of those plus 3 times 35.45. 162.2. I'm going to do 5.38 divided by my answer. Gives me 0.033 moles of FeCl3. I'm very happy to see that. The ratio is quite obvious. It's a 2-to-1 ratio. So we can now solve for the final answer. The formula for this hydrate is FeCl3.2H2O, because you can see there is twice as much water as there is iron 3 chloride. This is a dihydrate. Okay, good luck with your Hydrate Lab.